Today we will be talking about elasticity, or solid-like materials with high Deborah number measurements for polymer rheology and processing. So to review, the Deborah number, also known as D sub E, is equal to tau over T, where tau is the characteristic time of the material and T is the time of our experiment. Materials with a high Deborah number correspond to solid-like behavior, while materials with low Deborah numbers correspond to liquid-like behavior. And in general, if the Deborah number is well above 1, it's solid-like. If the Deborah number is about 1, it's viscoelastic. And if it's much below 1, it's considered liquid-like. So, solid-like behavior is when stress relaxation is long compared to the time taken to carry out rheological experiments. So to review, tau is the characteristic time of the material, and T is the characteristic time of the deformation process or our experiment. For our experiments, during the time scale of deformation, little or no relaxation can actually occur. So therefore, relative deformation or strain is recovered upon the removal of stress. We've seen this before when we talk about a Hookean solid. The shear stress sigma is applied to the surface results in an instantaneous deformation. Once the deformed state is reached, there is no further movement, and the deformed state persists as long as the stress is applied. And the relationship for a Hookean solid is a proportional one. In other words, sigma equals G, where G is the rigidity modulus, times the strain. Here we're going to define compliance and rigidity, and they're kind of opposite sort of terms. Compliance is the strain measured per unit of applied stress. In the compliance is the compliance of the material. If something is highly compliant, it has a large strain results from a small applied stress. Rigidity is the stress measured per unit of strain for the rigidity of the material. A highly rigid material has a small strain results from a large applied stress. For a simple solid material, measurements of strain as a result of applied stress can be plotted as a rheogram. For material that behaves in a simple manner, especially if strains and stresses are not too large, there's a linear dependence upon strain of stress upon strain. In other words, the material obeys Hooke's law, or sigma equals G times the strain. The implications are the material is isotropic, and the pressure on, in other words, the material itself is uniform, and the pressure on the material is also uniform for this type of relationship. So here we see another schematic of Hooke's law. The elastic modulus is constant at small stresses and strains, and the stress is directly proportional to strain, producing a linear relationship as you see here. Sigma times the modulus. Linear relationship. So, here's an example of an elastic material. And in this case, we're talking about vulcanized rubber. For vulcanized rubber, this was first introduced in 1839 by a gentleman known as Charles Goodyear, who was largely an unsuccessful inventor. Quite by accident, he discovered how to vulcanize rubber. And the term vulcanization actually comes from the Roman god of fire. There's a fun fact for you. So, natural rubber latex itself, or polyisoprene, is runny and sticky when warm and hard and brittle when cold. And these are things that don't make it very advantageous for, say, tires for your car. So the process of vulcanization creates bridges of short chains of sulfur atoms, and these tie the chains of polyisoprene together. When the rubber gets hot, the chains cannot flow past each other because of this, and that prevents melting. And because all the polymer molecules are tied together, they aren't easily broken apart, and that prevents embrittlement in the cold as well. So the process of vulcanization creates one giant molecule that is very elastic in nature. So, when an example of elasticity is the rheological response of vulcanized rubber. We can consider the normal stresses in this case, in other words, sigma xx, sigma xy, and sigma zz. And sigma xx is plotted against strain. The stress is calculated as the extensional force divided by the cross-sectional area of the sample at that extension. And percent strain is percent elongation as compared to the original length of the sample. And here we see that there is a linear relationship for a portion of this relationship. This is extensional stress versus percent strain. And this is stress versus strain for a typical elastomer of vulcanized rubber. And the straight line shows that a simple Hooke's law relationship would be observed at about 40% strain. In other words, approximately this region of the curve. So for vulcanized rubber, we can describe the response using one material constant, in other words, a rigidity modulus. And we kind of use a neo-Hookean model that can describe an elastomer behavior up to large strains. And we write the components of stress resulting from strain as what we see here. So sigma xx equals the rigidity modulus 1 plus modulus minus p, where sigma yy equals sigma zz, which equals this. So we assume P, which is pressure, is isotropic in this case. We also assume our material is incompressible. And the rigidity modulus G is what we should measure in a shear experiment. We can then eliminate pressure and come up with this particular term. So these are the pressure terms we had before from the previous slide. This is the relationship we can come up with now if we assume that pressure is isotropic. And since we're only pulling on the ends of the test bar, we can assume that sigma yy equals sigma zz, which equals 0. And if we work at small strains so that we are in the linear region of the rheogram, we get this relationship, shown here. So then, the extensional rigidity modulus, or in this case, Young's modulus, can be written in terms of the shear modulus. So, this relationship shown here. Generally, vulcanized rubber will be compressible, however, and remember we made the assumption that our material was not compressible. So then we have to introduce another material parameter, and this is Poisson's ratio. Poisson's ratio is defined as the ratio of the contractile to the tensile strain. So this relationship here then becomes this relationship, where Poisson's ratio is introduced. For an incompressible material, Poisson's ratio is 0.5. And we get this relationship back again. Rubber is usually fairly close to 0.5, but for many, many other solids, Poisson's ratio can be greater than 2.5 and less than 0.33. So we would have to apply this particular relationship instead for most other solids. We can also describe the bulk rigidity, K, in terms of Young's modulus as well, and Poisson's ratio with this relationship here. So bulk rigidity, Young's modulus, and Poisson's ratio. This concludes the first video in the elasticity high Deborah number measurements. Please come back for part 2 of this video. Thank you.